Hello everyone, my name is Shobha Sharma from ABES Engineering College, and in today's lecture we will discuss about semiconductor physics. Okay, so let us begin. Here we can see an atom in which this is nucleus around which there are various electrons in different orbits are revolving. Like in the first orbit, we can see there are 2 electrons which are revolving around this nucleus. In the second orbit, there are 8 electrons. In the third orbit, there are 18 electrons. In the fourth orbit, there are 32 electrons. And this last orbit is also known as valence shell. Okay, so here in the first orbit, there are 2 electrons which are associated with this particular energy level even. That means we have two 1s electrons which are associated with this particular energy level even. That means two 1s states are required to accommodate these 2 electrons, and these two 1s states which have these 2 electrons have energy levels which are very close to this energy level even. Okay, in the second orbit we have 8 electrons, out of which we have 2s electrons and 6 2p electrons. Okay, so these two different levels, 2s and 2p, that means 2s levels and 6 2p levels, have energy levels very close to this energy level E2. Okay, so we can say these 8 electrons are associated with this energy level E2 and so on. That means each electron present in an atom is associated with a particular energy level, a particular discrete energy level. Okay, so as we saw in the last slide, each electron in atom is associated with a particular energy level. Okay, so if we bring two atoms close to each other, that means the interatomic distance is very less. Then in that particular case, the same electron will not have the same energy state. That means these two electrons, that means if these two atoms will have sufficient distance between them, then these two electrons would have the same energy state even. Okay, but when we bring these two atoms close to each other to form an interacting system, then according to this particular principle, Pauli's exclusion principle, which says that in a single atom, no two electrons will have the same quantum numbers. That is, every electron should have or be in its own unique energy states. That means if we make a system in which two atoms are very close to each other, then these two electrons, which are same electrons, okay, so they will not have same energy states. That means this energy state E1 will split into two energy states, E1 and E2, okay, which will accommodate these two different electrons, 1 and 2. Similarly, for three atoms in an system, in an interacting system, the energy E1, that this energy state E1 will split into three different energy states, E1, E2, and E3. Okay, so to form a solid, when we bring n atoms close to each other, then this E1 state will split into n energy states. Okay, and these n energy states, this complete set of energy, different energy state is known as energy band. So whenever we talk about solid, we talk about energy bands. Okay, so this graphical representation will give you a clear understanding of energy band. Initially, when the interatomic distance is larger, that means two atoms or more than two atoms are having sufficient distance between them, then the corresponding electrons will have same energy state. They can have same energy state. But as we reduce the interatomic distance between atoms, okay, the energy state begins to split. Okay, and the number of energy state begins to increase as we further reduce the interatomic distance till this point, which we know as equilibrium interatomic distance. Further this point, we cannot reduce the interatomic distance. So at this point, you will get a clear picture of energy bands. Okay, so here we have seen that a single energy state, let's say E1, has been splitted into n number of energy states, which combine known as energy band. Okay, so let's take an example of an atom, carbon. Here we can see the carbon atom representation can be written as like this: 1s2, 2s2, and 2p2. That means there are two 1s states, two 2s states, and six 2p states. Okay, this 1s state is completely filled because we have two 1s states and two electrons. Okay, this 2s state is also completely filled because we have two 2s states and two electrons to accommodate these 2s state. There are two 2s states to accommodate these two electrons, and we have six 2p states, and only two electrons we have in these states. That means four states are empty. Okay, so each carbon atom has two 1s states, two 2s states, and six 2p states, out of which four states are empty, while the other two states are completely filled. Now, if we bring n carbon atoms close to each other to form a solid, then we have 2n 1s states, 2n 2s states, and 6n 2p states. Okay, so let's not talk about the lower states. That means below 2s states, we will not talk about the lower states because they will not participate in conduction. Okay, so let's talk about only 2s and 2p states. Okay, now at this point, okay, beyond this point, the distance between atoms was quite enough so that the energies associated with the electrons was same. Okay, the two corresponding electrons in two corresponding atoms of carbon were having same energy states, but as we reduce the interatomic distance between atoms, the energy states began to split. Okay, so we got two energy bands here and here. Okay, now then we further decrease the distance, interatomic distance, we decrease the interatomic distance. Then we saw that these two bands grow in size, and after this point, they merge with each other to form a single band. And in the single band, we have total 8 n states, 6 2p states, and 2 2s states, 6n 2p states, and 2n 2s states. So in total, we have 8 n states, while out of which only 4 n states are filled. Okay, 4 n states are filled. That means only 4 electrons are here in a single atom of carbon. We have only 4 electrons. That means in n number of atoms, we will have 4 n electrons. Okay, so out of these 8 n states, only 4 n states are filled. Now, with the further decrement of interatomic distance, we see this complete single band is splitted into two different bands. One is the completely filled band and one is the completely empty band. So this filled band where 4 n states are here and 4 n electrons are there to fill these states. So we call this completely filled band, also known as valence band. And the upper state, upper band is known as conduction band, in which 4 and empty states are here. Why they are empty? Because no electron is present in this band. Okay, so this is known as conduction band, and this filled band is known as valence band. And the gap between these two bands is known as energy gap. Okay. So on the basis of this energy gap, we will classify the solids into three categories. Okay. So this is a simple representation of energy gap and the bands. Valence band, conduction band, and the distance, or we can say the gap between the conduction band and the valence band is known as energy gap. Okay, so this valence band is a completely filled band because all the 4n states are occupied by the 4n electrons. And this conduction band is the empty band because all the 4n states are empty because no electron is present in this band. Okay, so on the basis of energy gap, we will classify the solids in the next slide. Okay, here we can see in the first category, which we are calling as insulator. In this first category, the gap and the energy gap between these two bands, conduction band and valence band, is greater than 5 electron volt, which is a very large gap. So it becomes difficult for the electrons present in this valence band to cross this barrier, to cross this energy gap to reach to the conduction band. And since no electron can reach to conduction band, the conduction becomes impossible. Okay, so in insulator, no current flows. In the case of conductor, these two bands, conduction band and valence band, they overlap with each other. That means the gap between them is 0. So we can say this is completely acts like a single band in which electrons are present. That means 4n electrons are present and 4n empty states are present. Okay, so these electrons can easily reach to conduction band and they can easily move through these empty states. And as we all know, conduction is possible only when electrons make a transition or when electrons basically move from one place to another place, or we can say from one empty state to another state. So in the case of conductor, this movement of electrons becomes the movement of this electron becomes very easy due to absence of the energy gap between these two bands, and hence conduction becomes possible. Okay. In the case of semiconductor, the energy Venn diagram, we can say that basically the representation of semiconductor is similar to insulator, except the fact that the energy gap between these two bands is of the order of 1 electron volt, which is a very small gap. So due to this very small gap, the electrons can easily move to conduction band from valence band. Okay, and when these electrons move from valence band to conduction band, they leave behind them empty state, which we known as hole. Okay, so the number of holes will be equal to the number of electrons moving to conduction band. Okay, so we can say in semiconductor, there are two types of charge carrier. One is electron and one is hole. Okay, electrons in conduction band and holes in valence band. So both of these charge carriers participate in conduction. Okay. Now, covalent bonds in semiconductor. Basically, before discussing about the types of semiconductors, we need to know the covalent bonds. We need to have a basic idea about covalent bonds in semiconductor. So here we have a crystal, silicon crystal. Basically, sorry. Here we have an interacting system in which we have n number of silicon crystals. Okay, so this particular silicon atom has 4 valence electrons, and they are, um, this particular silicon atom is sharing its valence electrons with its neighboring silicon atoms with the help of this bond, which we known as covalent bond. Okay, so using the covalent bond, these silicon atoms share their valence shell electrons with each other. Okay, now neighboring atoms form covalent bonds by sharing electrons with each other. So, in further slides, we will know basically that why are we discussing the covalent bonds. Okay, now types of semiconductors. There are two types of semiconductors: intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductors are also known as pure semiconductors. Okay, and extrinsic semiconductor are also known as doped, or you can say impure semiconductors. Okay, so first, let us understand what is intrinsic semiconductor. We will understand both these semiconductors with the help of energy band diagram. Okay, so first is intrinsic semiconductor. So in intrinsic semiconductor, if we say that we have taken the zero temperature at 0 degrees Celsius, uh, we see that no electron in valence band will gain the sufficient energy to cross this energy gap. Okay. However, the gap is very less, but electron needs at least a little amount of energy to cross this gap. Okay. Okay. So at zero temperature, no electron in valence band will gain that energy which is required to cross this energy gap. So current will be zero. No conduction will occur. As we increase the temperature, let's say at room temperature, okay, we assuming, let's say at room temperature, as we increase the temperature from 0 to room temperature, then we see some electrons gain some energy to cross this energy gap and reaches to conduction band. Okay, here, since there are various empty energy states are available, so these electrons will move through these empty energy states and conduction will occur. At the same time, these empty energy states, or we can say these holes which are left behind when these electrons made a transition from valence band to conduction band. So here also in valence band, we have some empty states. So the electrons present in the valence band, they will move through these holes or empty energy states. Okay, then conduction will occur. So we can say in intrinsic semiconductor, both these charge carrier, that means the electrons in conduction band and the holes in valence band, are participating in conduction. Okay, also the number of electrons in conduction band are equal to number of holes in valence band. Okay, so this case is valid only in intrinsic semiconductor. Now, whenever we talk about semiconductors, we often take only two types of crystals like silicon and germanium, but silicon is preferred over germanium in the maximum cases. So here are three reasons why do we take or why do we prefer silicon over germanium. First is silicon has better thermal properties compared to germanium. The maximum operational temperature for germanium is 80 degrees Celsius, while for silicon devices, it is up to 160 degrees Celsius. So the operational temperature range is better for silicon. Now at room temperature, silicon crystal has no free electron compared to the germanium crystal. Okay, so we can say that at lower temperature, silicon conducts very well compared to germanium crystal. So silicon is a better choice compared to germanium. Okay. Now, second type of semiconductor is extrinsic semiconductor, which we also known as doped semiconductor. Okay, so there are two types of extrinsic semiconductor, N type and P type, depending upon the impurity we are adding to the conductor. So in N type semiconductor, we add pentavalent impurity. Okay. Pentavalent impurity to the semiconductor. Pentavalent impurities are those impurities which have 5 electrons in their outermost orbit. Okay, or in valence shell. So basically what happens? Out of these 5 electrons, 4 electrons make covalent bonds with the silicon atoms. For example, there are six, sorry, 4 silicon atoms, neighboring silicon atoms, and we are adding a pentavalent impurity, let's say antimony. Okay, let's say we are adding antimony, which has 5 electrons in its outermost orbit, out of which 4 electrons are making covalent bond with the neighboring silicon atoms, and one is a very loosely bound electron. Okay, it is a loosely bound electron, and it needs very a little amount of energy to to reach to conduction band. Okay, so we can say the donor energy level. Donor, why we are calling it donor atom? Because it is donating a charge carrier. So the donor level has energy level very near to this conduction band. That means the gap between the conduction band and the donor energy level is very less, is a very little gap. Okay, so it is very easy to reach the electrons. That means this particular electron at this donor level to it is very easy to to reach the electrons present at this donor level to conduction band. Okay, due to this very small energy gap. So we can see the number of electrons present in conduction band which are reaching here from this donor level are very large in number compared to the electrons which are reaching from the or which are coming, actually which are coming from the valence band. Okay, so if we compare the number of electrons in conduction band and the holes in valence band, we see the number of electrons in conduction band is very, very, very large compared to the holes in valence band. And that's why we say that electrons are majority charge carriers in N-type semiconductors. Okay. And the holes are minority charge carriers in N-type semiconductor. Now, second case is of P-type. In this case, we add trivalent impurity. Trivalent impurity means which has 3 electrons in its outermost orbit. So it's obvious that these 3 electrons will make, that means they will participate in covalent bond. That means they will, this particular impurity, let's say aluminium. Okay, it has 3 electrons in its outermost shell, out of which, okay, these 3 electrons, this aluminium will share its 3 outermost shell's electrons with the neighboring silicon atoms. Okay. But here it's a empty state. Okay. So it's an empty state, or we can say it is acceptor impurity. That means it can accept the electron. Okay. So the energy level of the acceptor atom is very near to the uppermost energy level present in valence band. So due to this small energy gap, the electrons present in valence band will easily reach to this acceptor level. Okay. While very few electrons, very, very few electrons will be able to make it to the conduction band. Okay. So we can say here in P-type semiconductor, the electrons are minority charge carrier, while the holes in valence band are the majority charge carriers, due to which the conduction will occur. Okay. Because there are very, very large number of empty states present in valence band. So the electrons will move through these empty states, and conduction will occur due to these holes. Okay. So this was all about semiconductors. Here are some references. Thank you.